Hello again. Any question or any queries regarding the lectures and the tutorial problems? If you have any question, we can discuss now, or I will start the solutions. Any question? Okay. We have two questions for tutorial this week. Okay. The first question, we have a system of several springs. We have two rotational springs and three linear springs. We want to obtain the equivalent spring constant for this system. You can obtain the equivalent springs using different methods. I mean, for example, here you can assume that KT1 and KT2, for example, are parallel, then find their equivalent stiffness. Then here K1 and K2 and also are parallel. K3 has a specific displacement. But if you want to use the usual method to obtain the equivalent stiffness here, because this is a combination of rotational and the linear springs, it's to somehow impossible to use the usual method. In this type of problems, the best option is using the energy. You can obtain the total potential energy for this system, and then you know that the potential energy for this system is equal to half times by the equivalent stiffness times by theta squared or x squared, for example. Because this is a system with a single degree of freedom, and we can assume the theta as a single degree of freedom for this system, we can write the displacement of this point for K3 and this point for K1 and K2 as a function of theta. So you can see this is a system with only 1 degree of freedom, because you can obtain the displacement of each point as a function of theta. For example, for K3, for this point, the displacement is equal to L2 times by theta. And for this point, for K1 and K2, the displacement is L1 times by theta. So all of the displacements are functions of theta. And for KT1 and KT2, it's clearly the displacement is angular and it's equal to theta. So the potential energy for this system is equal to the summation of the potential energy in KT1, KT2, K1, K2, and K3. Because we have 5 springs, so the potential energy is the summation of 5 springs. The first one is half times by KT1 theta squared, half KT2 theta squared for these two rotational springs. For K1 and K2, as I told you, they are parallel, so it will be half K1 plus K2 times by the displacement of this point, which is L1 theta squared. And finally, the last spring, which is K3, is half times by K3 times by its displacement, which is for this point, and it's equal to L2, the length, times by theta squared. So you can simplify this term, and finally you can conclude that half times by K equivalent times by theta squared you can extract the equivalent stiffness for this system, which is KT1 plus KT2 plus K1 plus K2 times by L1 squared plus K3 times by L2 squared. So this is the equivalent stiffness for this system. Is it clear? Any question? No question? Okay. The second problem is two different ordinary differential equations. The first one, here we have, you can see we will have y double dot plus y dot minus 6 times by y is equal to 6 times by 3 cubed minus 3 times by t squared plus 12 times by t. So this is a non-homogeneous equations from order 2 with non-homogeneous terms, which is a polynomial from order 3. So we need to obtain first the homogeneous response and finally the particular response. The homogeneous response for this system can be obtained from the characteristic equations. We can form the characteristic equation. You can see the characteristic equation for this equation is alpha squared plus alpha minus 6. It's equal to 0. The coefficient of y double dot is 1. So the coefficient of alpha squared is 1. The coefficient of y dot is a 1. So the coefficient of alpha is 1 as well. And plus the coefficient of y, which is minus 6. So here we will have minus 6. So this is an algebraic equation from order 2. Easily using the delta method, you can obtain that alpha 1 is equal to 2 and alpha 2 is equal to minus 3. So the homogeneous response is C1 exponential alpha 1t plus C2 exponential alpha 2t, which is 2 and minus 3. For the particular response, as I told you here, you can see we have a polynomial from order 3. So the particular response for this part is equal to a polynomial from order 3. As you can see, d3 times by t cubed, d2 times by t squared, d1 times by t, and d0. We need to obtain d0, d1, d2, and d3 by plugging in to the equations. For this purpose, we need to find a y double dot, y dot, and y, which is this term, and substitute here and simplify and solve this equation to obtain d0 to d3. So for this purpose, we can find these terms. I think I can use, because here I don't, it's not a face-to-face tutorial. I will use a software to show you how to calculate the derivatives and how to substitute into the equations. So let me show you in one software. Okay. Can you see now my desktop? Yes?
No, sir.
So let me stop and again share. The equation is y double dot plus y dot minus 6y is equal to 6t cubed. Here. Okay, can you see now?
Yes, sir.
Okay, so the equation is the derivative. Of course, this is Maple. I just use this software to show you how to calculate the derivatives and how to substitute into the equation. I mean, you don't need to use this software. I just want to show you what is the procedure. Okay, you don't need to know how to use this software. I show this command diff, which is the derivative command in Maple. The equation was the second derivative of yt. Here we show the derivative, the second derivative of yt. Here you can see using this command in the Maple. The equation was the second derivative plus the first derivative of and minus 6 times by yt. And the non-homogeneous term in the right hand side was 6t cubed minus 3t squared plus 12t. When you move these terms into the right hand side of the equation, it will multiply with one negative. So instead of 6t times by t cubed, it will be minus 6 times by t cubed. Minus 3 will be positive, so it will be plus 3 times by t squared. And finally plus 12, which is minus 12 times by t. So this is the equation that we need to solve this equation. The first part, we solved the characteristic equations, which was alpha squared plus alpha minus 6, and we obtained a homogeneous response. The characteristic equations was alpha squared plus alpha minus 6. This is the characteristic equations. If you solve these equations, the roots was 2 and minus 3. So the homogeneous response, we assume that the homogeneous response is equal to C1 times by exponential of 2 times by t plus C2 times by the exponential of minus 3 times by t. This is the homogeneous response, and C1 and C2 these two constant coefficients will be obtained from the initial conditions. But now we want to obtain the particular response. I told you the particular response will be considered as D0 plus D1 times by T plus D2 times by T squared plus D3 times by T cubed. So this is the particular response. And now I want to substitute this yp into the main equation and simplify and solve this equation to obtain D0 to D3. For this purpose, we need to calculate the second derivative of yp, the first derivative, and the yp, which is this term, we can substitute here. So for this purpose, I will substitute yt is equal to yp into the equation. If you substitute this term, you can see this is the main equation. Instead of yt, instead of this term, I substitute yp. So it's the second derivative of the yp, which is this term, the first plus the first derivative, minus 6 times by the yp, and minus 6 again, minus 6t cubed here, this term, plus 3 times by t squared and minus 12t. Now we can simplify this equation. Of course, you can do it manually here because it's Here I don't have access to the whiteboard and I cannot show you how to simplify this equation. I'm using this software, but you can use it manually, okay? So simplify this equation and we can collect this term for t. You can see we will have this, the coefficient of t cubed, the coefficient of t squared, the coefficient of t, and finally the coefficient of t to the power of 0, or the constant part. All of these terms must be equal to 0 because yp is your answer. When you plug in your answer into the main equation, it means that the equation should be satisfied. When you substitute the solution into your equation, this equation must be equal to 0. For this purpose, the coefficient of t cubed, t squared, t, and this constant term must be equal to 0 separately. So we will have 4 equations. The first equation is the coefficient of t cubed. The second equation is coefficient of t squared. The third equation is the coefficient of t. And finally, this is the last equation, minus 6d naught plus d1 plus 2d2. So we will have 4 equations. I will call them the first equation, which is this term. The second equation, which is the coefficient of t2. The third equation is the coefficient of t. And finally, the fourth equation, the last one, is this term. So we have 4 equations. You can see minus 6d3 minus 6, the coefficient of t cubed. Of course, you can, as I told you, you can easily solve these equations manually. Here I'm using this software because I want to show you the procedure, okay? For example, from the first equation, from the coefficient of t cubed, you can easily obtain d3. Then you can substitute here and you can obtain d2, then substitute here, obtain d1, and finally from this equation you can obtain d0. Now I will solve these 4 equations. E1, E2, E3, and E4. We have 4 equations with 4 unknowns. Okay, you can see we have 4 equations, E1, E2, E3, and E4 with 4 unknowns. We will solve these 4 equations with 4 unknowns. D0 is minus half, D1 is minus 3, D2 is 0, and D3 is minus 1. So we will have 4 constants. And now you can substitute this coefficient into YP. If we call it, for example, the solution, we can substitute the solution into the YP. And this is your final response. If we call it, for example, YYP, this is your response. And finally, the total response is equal to the particular response plus the homogeneous response. So this is the total response. And now we can use the initial condition to obtain C1 and C2, which initial conditions, I think we should again refer to the problem. Okay, so is it clear this procedure, how to obtain the coefficients in the particular response? Any question from this part? Any question? No questions? Okay, we continue. So you can see we obtained D0 to D3. And we can substitute and solve for initial condition. The second problem here is this equation with initial condition 0 and 2. We need to form the characteristic equation. This is the characteristic equations. Alpha squared plus 9, it's equal to 0. So the two roots for this equation is plus minus 3i. So the homogeneous response is C1 cosine 3t plus C2 sine 3t. And the particular response here, we have two different harmonics. The first one is frequency 1, and the second one is with frequency 3. As you can see, the frequency of the non-homogeneous term is as the frequency of the system or the natural frequency. In vibration, we call it resonance, or this is a secular term. For this purpose, to obtain the particular response, we will have a coefficient T in to the particular response. So the particular response will include two different parts. The first part is due to the frequency of 1, and the second part, which is due to the frequency of 3 with a coefficient T, which this T is because we have the same frequency in the natural frequency. So of course, this is a mathematical method, but in the vibrations, we can see the effect of this T will be seen in the response. When you plot the response, you can see the amplitude of the response will increase by time, and it's not bounded. So we can plug in this YP into the main equation, similar to the part A, and obtain D0, D1, D2, and D3. And finally, by using the initial condition, we can obtain these two constants, C1 and C2, which are the constant coefficient into the homogeneous equations. Okay. Any question? If it's clear and you don't have any question, we can wrap up this session. No question? Can you hear me clearly?
Yes, sir.
Okay, so don't you have any questions?
No, sir.
Okay, thank you for your attention and have a good day. Thank you.